DNA. Technology behind DNA chips. In the form of DNA, nature demonstrates how data can be stored efficiently and for an extended period of time. The bioinformatics professorship at Würzburg is developing DNA devices for computer technology. DNA is renowned for its ability to store immense quantities of information over extended periods of time in a minuscule quantity of space. For a good 10 years, scientists have therefore been pursuing the aim of developing DNA devices for computer technology, particularly for the long-term archiving of data. These processors would outperform silicon-based chips in terms of storage density, durability, and sustainability. A DNA strand consists of 4 repeating fundamental construction elements. As in nature, a specific sequence of these blocks can be used to encode information. The correspondingly coded DNA must be synthesized and stabilized in order to construct a DNA chip. If this method is successful, the information will be preserved for a very long time, several thousand years, according to researchers. It is possible to retrieve the information by mechanically reading and decoding the sequence of the 4 fundamental construction elements. Problems with DNA data storage. Professor Thomas Dandeker, Chief of the Chair of Bioinformatics at Julius Maximilians Universität, JMU, Würzburg, asserts that digital DNA data storage with a high capacity and a long longevity has been repeatedly demonstrated to be possible in recent years. However, storage is expensive, costing close to $400,000 per megabyte, and information contained in DNA can only be retrieved slowly. It takes anywhere from hours to days, depending on the quantity of data. These obstacles must be surmounted for DNA data storage to become more applicable and marketable. Suitable instruments include light-controlled enzymes and software for designing protein networks. In a recent review for the journal Trends in Biotechnology, Thomas Dandeker and his county chairs Aman Akash and Elena Benkurova discuss this topic. The crew of Dandeker is convinced that DNA has a future as a data storage medium. The JMU researchers demonstrate in the journal how a combination of molecular biology, nanotechnology, novel polymers, electronics, and automation, coupled with systematic development, could make DNA data storage practical for everyday use within a few years. DNA chip innovation. Dandeker's team at the JMU Biocenter is developing DNA circuits composed of semiconducting nanocellulose generated by bacteria. The professor explains, with our proof of concept, we can demonstrate how current electronics and computer technology can be partially replaced by molecular biological components. On this basis, sustainability, complete recyclability, and high robustness against electromagnetic pulses or power failures could be attained, as well as a storage density of up to 1 billion gigabytes per gram of DNA. Thomas Dandeker considers the development of DNA chips highly significant, stating, "We will only survive as a civilization in the long run if we make the transition to this new type of sustainable computer technology that combines molecular biology with electronics and new polymer technology." What is essential for humanity, he said, is to transition to a circular economy in harmony with planetary boundaries and the environment. We must accomplish this within 20 to 30 years. Chip technology is a prime example, but the sustainable technologies required to produce semiconductors without generating e-waste or contributing to environmental contamination are not yet fully developed. Our nanocellulose device concept contributes significantly to this goal. In the new paper, we analyzed our concept critically and advanced it with recent research developments. Strengthening DNA storage media. The team led by Dandeker is presently working to improve the compatibility between the DNA circuits made of semiconducting nanocellulose and the designer enzymes they have created. Additionally, the enzymes require further improvement. In this way, we hope to achieve better and better control of the DNA storage medium and be able to store even more information on it, while also reducing costs and thereby gradually enabling its practical use as a storage medium in everyday life. Thanks for watching. Please do not forget to subscribe.